Let's start today's lecture. So we are going to continue the Sudoku problem, and there's another puzzle called Number Snake. Okay. So we talked about this Sudoku puzzle before, and this was the rule that I didn't ask you to write, but basically the rule was giving that if you fix any box, then you place number 1 through 9 to each of the box. That's what the first rule was saying. Okay, so we talked about this before. And there are other constraints that we said. So given the row and number, you shouldn't have two different columns. So they're actually all the combinations. So if you have columns and number, then you shouldn't have two different rows. If you have row and column, then you shouldn't have no two different numbers. So if you fill all these things, then you can formalize Sudoku in Clingo. Now, maybe just a hint for the homework. If you want to do 16, then some number has to be changed. 16 by 16 Sudoku, you're changing it, right? For all the other Sudoku problem, you don't need to change the basic code. Something that you may have to change is, of course, the instance, because the problem itself can be given different ways. So here we say 1, 1 position, there's a number 9, and so on and so forth. Okay, so this is something that you have to type in. And if you are interested, you can actually, somebody was doing this task, which was not assigned, but somebody did it by reading from the picture to convert into ASP format. So somebody did that for fun, actually. And another student actually did this project, which was, so here I teach you how to solve the Sudoku, but you can actually generate Sudoku puzzle by inverse way of doing this. So you can actually write a Sudoku generator. Okay? So you can also publish a Sudoku puzzle too. All right, so that's what we saw before, and this is the homework problem. And one of the homework problems, why this is hard? I imagine that this is because there are so many possibilities there for some places. But in fact, from computer point of view, well, you can try. Okay, so try this and see whether this is really hard for computer to solve. Okay. 16 by 16 Sudoku. Okay. So that's yet another one. So what I'm going to tell you today is about so-called elaboration tolerance. This was the quote by John McCarthy, who is a founding father of AI. And he was saying that formalism is elaboration tolerant to the extent that it is convenient to modify a set of facts expressed in the formalism to take into account new phenomena or changes circumstances. So we are actually good at the modifications, but the machines are not so good at. Okay, so AlphaGo that works nicely for 19 by 19 board doesn't work well if you have 20 by 20. Okay, but we are actually good at it because we can use the heuristics that we learned from one domain to transfer to another. Representation of information in natural language have good elaboration tolerance when used with human background knowledge. So this is where we are better than machines at this point. And he was also saying that human level AI will require representations with much more elaboration tolerance than those used by present AI programs, because human level AI needs to be able to take new phenomena into account. Okay? This is actually the big problem with autonomous vehicle. When it doesn't see from the data, but it may crash. It may encounter new scenarios, and it may crash. Okay? But anyway, we're not going too deep into that kind of thing. But what I want to show you today is how we can solve variants of Sudoku without actually changing the basic formalization. So you may think if I have to write another program for solving another variant of Sudoku, I have to change a lot of code in my Java program. It doesn't happen that way if you use Clingo. So here is the one of the variations called offset Sudoku. So it takes all the basic requirement plus additional requirement that if you look at the positions, okay, in this box, so there is a relative position in the box. And for that position also makes certain regions to think about. So for instance, here, this is 1, 1 position of each of these 3 by 3 box, right? Not this one. Okay? So I put the 1, 1 position, and this gives 9 positions, and you have to place 1 through 9 exactly once in these positions. Same for the next positions, and so on and so forth. Okay? Are we together? So what can you do? Can you solve this problem? Actually, if you try to solve this problem, will it be easier than the basic problem that we talked before, or will it be harder? If you're trying to solve this problem, will that make the problem harder? Will you like to solve this problem over the basic problem? Right. So you actually have more information. You just need to use that information. Okay? And in fact, if the computers are given this test, they work actually faster. Okay? So here is the solution. As you see, this position, okay, 1, 6, 8, 2, 5, 4, 3, 9, 7, they make the valid configuration. You can actually take the middle box, 2, 5, 4, 9, 6, 1, 7, 3, 8. Okay, remember when we did 6 by 6 Sudoku, we look at one constraint, right, in the row constraint or column constraint, or box constraint, right? We do 1 by 1, right? Now this time we actually have 4 constraints. So we look at the row conditions, column condition, box condition, as well as this region condition. Okay? So this gives more information for us to process. So this actually makes the problem easier. Okay? Mentally, that might be different. Okay? You seem to think that, well, there are more things that I have to worry about. It's not. Actually, it gives more information. So how do we solve this Sudoku puzzle in Clingo? So I told you, do not touch the base program that I showed you before. We are only going to add one more rule here. And the rule here is saying this. So there are 2 positions, R, C, that has the value n, and R1, C1, that has the value n. So these are the 2 positions that have the same value n, okay? But remainder of R when it's divided by 3 is equal to the remainder of R1 when it's divided by 3. And same for the columns. Then this violates the constraint. So what does that mean? So if you look at this, let me actually try 1, 1, and this one is 4, 7, right? 1, 1 and 4, 7 belongs to the same region. How do we check that? So 1, 1, okay, and 4, 7, okay. So R divided by 3. What is the remainder when you divide R by 3? By the way, what is the remainder? Okay, you divide it, and then something remains, right? What is 5? The remainder of 5 when it's divided by 3? 2. What is the remainder when 6 is divided by 3? 0. True. So same here. So when you divide 1 by 3, the remainder is 1. So this is 1. What about 4? 4 divided by 3, the remainder is still 1. Okay? What about here? C divided by 3, when C is 1. Okay, that's 1. 7 divided by 3, the remainder is still 1. So you can check any position in the same region will have the same pairs of value when you look at the remainder when it's divided by 3. Okay? You can check more things. So we checked 1, 1 and 4, 7 is the same. But let's actually try something different. What about 5, 2? Are they in the same region? Hmm? 1, 1 and 5, 2, are they in the same region? This could be a good quiz for next time, right? I gave you a bunch of the pairs and see which are they in the same region, right? So 1, 1, 5, 2, are they in the same region? So let's check it. So R is 1 and C is 1. R1 is 5, C1 is 2, right? So 1 divided by 3, the remainder is 1. 5 divided by 3, the remainder is 2. So this is not true. So this constraint is not violated. So they are in different regions, so we don't have to worry about whether they have the same number or not. Okay? So the constraint is saying if R1, C and R, C and R1, C1 have the same digit and they are in the same region, then this violates the constraint. That's what exactly this variation is supposed to do. Okay? Question, is this correct? I left out one bug in this code. There is a bug in this code. Somebody who doesn't have the participation credit. Don't you have it? Okay. Right. If they are the same positions, obviously they have the same number. We don't want to exclude them, right? True. What is your name? What is your name? Tyler. Okay. All right. So Tyler is correct. When this is actually the same number, then obviously so say 1, 1, for instance, right? I mean, that's okay, because there's only one number that you can associate in each position, so they should have the same number. We don't want to say that this violates the constraint. But once you do that, then what do you expect as a stable model? What do Clingo will say if you type this way? Tyler, what the Clingo will output if I give this code? There should be no stable model, because every stable model will violate this constraint. That's too much. Good. Okay. So the correct answer is these positions should be different. How do we say this is different? It's a one way. Okay. So we say either R is different from R1 or C is different from C1. And there's a lower bound 1. So meaning that at least one of them is true, right? So when R is different from R1, we don't care about the C. C can be the same, but still they represent different positions. Same way, C is different, then even though R is the same, then that does not make, that is okay. So what I'm saying is, for instance, we can have 1, 1 and 1, 4, right? These are the same region, right? Their row numbers are the same, but they are still different positions in the same region. We can have, of course, different things. So we can have 1, 1 and 4, 7 example. So rows are different and also columns are different. That's okay, because the low bound is 1. So at least one of these inequalities is true, then we are done. So there are 3 possibilities. R is different from R1. But C could be the same, or C could be different and R could be the same, or R and C's are all different. Okay? All right. So this is it. Actually, I don't have any other things to say. This is the old solution. Okay. Now let's look at the next puzzle, which is anti-nice Sudoku. So here the question is, so in addition to the basic requirement, we also have the requirement that you cannot have the same number in the night position. So night goes maybe 2 positions vertical and 1 position horizon, or 2 position horizon and 1 position vertical, right? So for instance, if we place 6 here, that means these 8, 9 positions cannot have the same number 6. Okay, so as you see from this solution, when you see this, there's a 6. So 8, 1, 9, 5, 9, 5, 4, 7. Yeah, they don't have the same number 6. That actually makes another kind of region because there are 8 positions surrounding one number. So they make 9 positions. Okay? So let's pause here and think about how to solve this problem. How can we solve this anti-nice Sudoku problem? Again, we do not want to touch the base program, right? We just want to add one more rule. Actually, one. I don't mind, actually. You can add more rules, as many as you need. Okay? So, what can we do? Well, the idea is, let's do some silly way first. Okay? And then I'll ask you some quiz. Okay? So here's the base program. What we say here is, let's say we have R and C has number n. And then R minus 2 and C minus 1, that's another position which is in the night move, right? And they also have the same number n, then this violates the constraint, right? So what we are doing here is to create all possible night move. So it could be R minus 2, C plus 1, R minus 1, C minus 2, R minus 1, C plus 2, R plus 1, C minus 2, R plus 1, C plus 2, and so on and so forth. Okay? So this is all possible move that can go from R comma C. Right? Are we together? One question that you might ask is, what if R is 1, 1? Then what is R minus 2? It's actually A of, so this becomes A of minus 1 and C of 0. Do we have such position? No. But do we care? We don't need to care because A minus 1, 0 will not be given as a fact. So this rule will never be violated. Okay. Remember, in addition to the basic formalization, we give the instance, right? A 1, 2. Okay. So we give this instance. We never give A minus 1, 0. This is never true. Okay. This can never be true. So the outer bound has no problem. Okay. If you worry about it, you can also write some conditions, but that's redundant. But there is actually a better way. There's one rule. Okay, so here we say R comma C has n, R1 comma C1 has n, and the absolute value of the row difference plus absolute difference of column difference, right, equals 3. Then this violates the constraint. So instead of using these 8 rules above, you can just write one rule. Now the question. Are they equivalent? I said that you can add either 8 rules or maybe you can add this rule. But do they really do the same thing? Do they constrain the problem in the same way? Do they have the same meaning? So let's actually, before we answer that, let's check this thing. So why this equation makes sense? So we say that, let's say a 1, 1, okay, and a maybe 3, 2, okay, that's in the night position, right? Okay, because 1 plus 2 and 1 plus 1, okay, so that's night position. And this night position, which is actually coming from maybe this one, right? So this is an instance of it. Now this is actually covered by this because R1 minus R is 2, and C1 minus C is 1, and 2 plus 1 is 3. So it is covered. But do they do the same thing? Okay, so let me open the chance to anyone. You can, don't you have credit? You don't? Okay, so what is your answer? More. So what are the more case? R1 is equal to R, C1 is equal to C. Well, then this is not true, right? Let me ask you this way then. What is the more case? Can you give a particular example that is covered maybe here, but not covered here? Just give one example. Just I need only one pair of R, C and R1, C1. That's enough. Okay, I think let's move on to maybe next person who may have answer. Those who doesn't have credit. Okay, what about you?
The bottom one and the check 8, pretty much all spaces.
Can you give one example that is covered by the bottom rule but not covered by the eight rules above? Just give one example of R, C and R1, C1.
1, 1, and 1, 2.
1, 1 and 1, 2. Okay, let's check about it. So 1, 1 and 1, 2. Well, so R1 minus R is 0. 2 minus 1, C1 minus C is 1. So this is actually not true. So we don't need to worry about this case. And this case does not arise in any of the 8 possibilities, right? You cannot actually make this as an instance of one of these. So this doesn't seem to be the right one. I think you have credit, right? You don't? You don't think so? How about you? Do you have credit? Rock, paper, scissors? Okay, rock, paper, scissors. Go. Okay, one more time. Okay, rock, paper, scissors, shoot. Rock, paper, scissors, shoot. You got it? Okay, okay. Okay, so again, the same question to you. Can you give one example that is checked here, but not checked here? Just one example.
1, 1, and 1, 4.
Aha! Okay, so let's look at that. Let's erase many other things that is not needed. So, what is your name? Ty. Tyler and Ty. Okay. So what Ty is saying is, what about 1, 1 and 1, 4? Okay, so first let's see whether this is checked by any of the 8 rules. No, not at all, right? So any of the 8 rules, when R is 1, the second one is either R plus 2 or R minus 2 or R minus 1, R plus 1. It changes, right? But here, this is R1 minus R is 0. C1 minus C is 3. Done. So it checks more if you just look at the upper rules versus the last rule here. Are we doing something wrong then? Because we are supposed to only worry about anti-night Sudoku, right? So only the anti-night position, we shouldn't have the same row. Isn't it dangerous to do? It's actually more than anti-night movement, right? Why is it okay to do this? That's also the question. Why? Ty, you have some idea, right? No? Okay. Do you want to give chance to other people? Okay. Good boy. All right. So the next question, why is it okay to do this way? Why is it still safe if we check more than this? It's not supposed to check these things, right? You again.
That rule is already covered by the row or column.
Okay, what's your name?
Lathan.
Lathan. So Lathan says it's already checked by the another rule, which was given last class, right? So it's actually redundant. But this redundancy actually helps us to write the rule in a short way. Okay? Now look at this, 1, 1 and 1, 4. That means actually you cannot have the same numbers in the same row, right? In the row position, row 1, you cannot have two different, when in the row position, but this different column, you cannot have the same number. But that's already covered by the one of the rules that we saw before, which is okay. So there are some times that, personally, I think the first 8 rules are easy to understand, but it's verbose to write. If you think a bit more, it's a bit indirect, but it is short. Okay, so this kind of trade-off is happening a lot when you formalize the program. All right, good. So then let's move on to the next problem. So this is the greater than Sudoku problem, which is probably the puzzle that I don't want to solve by myself. Okay, so what you're given is the clues that this position, the number in this position should be bigger than the number here. So we are only given the relative inequality between the two positions, but we don't have any numbers filled in. Okay? How can you solve this problem? I don't know whether people actually play with this example. This is the solution, okay? And as you see here, if you look at these two positions, okay? So 3 is bigger than 2, okay? And these two positions, 9 is bigger than 3, okay? So you can actually check that all these positions actually satisfies the requirement, in addition to the basic requirement. Okay? So how do we solve this one? Anything, Thomas? Some comment? No? Okay. You want to solve this? Okay. Yeah, Nathan.
Add more rules and invalidate cases where it violates the greater than.
Exactly. Good, good. So that's what we will do. So in order to do that, we need to actually introduce new predicates saying greater than. So greater than means the number that we put in the R, C position should be greater than the number in R1, C1. Okay? So that is something that you have to give as an instance. So for instance, for here, we can say that this is GT of 1, 2 is bigger than actually 1, 1. Okay? Unfortunately, there's no simpler way than this I can think. So that means you have to encode all these instances by yourself. Hopefully that is much better than writing the rules from scratch. All right, so what we are going to add is having this instance given, okay? This input is given. What we are saying is, if you have R, C that has number n, and R1, C1 has value n1. But if n is less than or equal to n1, which violate this greater than relation, then it violates the constraint. Then you're done. There's only one rule that you write to solve this problem. And the ugly side is you have to write these many GT predicate. So that's not so fun. That's why some people want to invent automated program. But for your homework, I don't know whether this is better to do. Okay. All right. Any question up to this part? You're welcome to write some image recognizer in neural network and classify this. That might be interesting project by its own. Okay, how are we doing? All right, good. The next one, so going through this grid puzzle, like Sudoku, I have one more problem. And this introduced yet another feature of Clingo, so that's why I want to go for that. This is a number snake puzzle. I don't know whether you have solved this puzzle before. It's also known as hidato in Japanese. And here the numbers, you have to place 1 through 9. But then this number has to be connected. Here the connection is either one consecutive row or the column or diagonal. Okay? So let's actually play with this example. Okay, so this is the 1. Okay, so starting with 1, let me change the color. Okay, so this is 1. So I can go 2. Okay, so where do I place 3? So 3 has chance to be placed in nearby, so it could be here, 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 here. Right? Actually, it's all possible because it's from the middle. Let's try this one. So let's place 3. Then I have to place 4. And the only 2 places that I can place 4 is either here or here. But if I do 4 here, then it seems to be dead end. So maybe let's try to do 4 here. And then the question is, I have to place 5. Then this is the only place. Well, it doesn't work because now 5 and 6 is not connected. So this is a bad choice. We have to backtrack. Which is the place that we have to backtrack? It's actually this 3. Then where do you put? Well, let's put 3 here. Actually 3 here. It doesn't actually work too. Okay. So you will see that if you do this, 4 can be placed here. No, actually maybe. If you have 3 here, 4 should be here. If 4 is here, then 5 is here. 5 is here, then 6 here. The problem is I don't know where to put 7. So this does not work either. Okay. So what I'm showing you is so-called depth first search that I can do this in any AI code. So these 2 positions didn't work. So I'm trying 3 here, okay? And then I have another choice, either 4 is here, here. Okay, I'm lost. I can do that, but that's not so fun. So maybe let me ask some of you to help me. Okay, so did you solve while I'm mumbling? Okay, Oscar? Yeah, what number should we put? Just tell me.
3 on the bottom right.
3 on the bottom right.
And to the left of that would be 4.
Okay.
And then next to the left of 2 would be 5.
Mm-hmm.
And then to the right of 6 would be 7.
Ah, okay. So let's check whether this is the solution. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so I did it. Okay, so this is the solution. Now, the participation credit problem. What about this one? This is now 4 by 4. I'll give you 2 minutes to think about. Well, anyone can raise hand if you got it. Done? You again? Okay. All right. Maybe you're good at this puzzle. Okay, so why don't you tell me the numbers? 1, 16, and then just write it here. What should I do?
I'll just tell you. So below 16 would be 2.
So can you just tell me just row by row? Yeah, that'll be easy. 1, 16, and then
16, 3, 5.
3, 5,
And then 15,
15,
2, 6.
2, 6,
And then 14, 7, 11.
and then
And then 13, 12, 8.
Okay, so let's check whether this is the solution. So from 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Done. Okay, Oscar get the credit. Okay, so how do we solve this puzzle in Clingo? Maybe I should have given 5 by 5. All right, number snake in Clingo. So same as before, let's try to formalize it. So here we have n by n grid, and we have to place the number from 1 to n square, right? Okay, all position has to be occupied. So what do we do? The first line is the generate part. Okay, so here we have R and C that goes from 1 to n. And then we have to place the 1 through n square. But you have to use exactly one number from 1 to n square. So by now this should be familiar to you. Okay, so this is the global variable. When you fix the value of R and C, okay, you have to place this number, exactly one number from this, into that position. Okay, so even though I write one line here, okay, if n equals 3, then there will be 9 rules. Okay, when R equals 1, C equals 1, R equals 1, C equals 2, R equals 1, C equals 3, R equals 2, C equals 1, R equals 2, C equals 2, R equals 2, C equals 3, R equals 3, C equals 1, R equals 3, C equals 2, R equals 3, C equals 3. There are 9 rules. And for each 9 rule, you have to give exactly one number from 1 to 9. Okay? Does it make the solution for the number snake? Obviously not. It's just you put a number from 1 to n square into this n by n grid. Okay? But if you're lucky, you will see the solutions in there. Now, something that we want to say is we should make sure that every number between 1 to n square is included. We should not miss any of the numbers. And here we use actually a bit interesting feature, which I'm going to explain a bit moment. You see sometimes Clingo use the underline, which is called so-called anonymous variables. Okay? So this is the variable that we don't care its name. Okay? So what this rule is saying is I don't care about the positions r, c, but each number from 1 through n must be filled in. That's the rule, what the rule is doing. So once you give this, you are giving the assignment from one-to-one correspondence between the row and column pairs to the digit. Okay? But that's not enough, because we have to worry about here. The main problem here, this is actually similar to the other problems that we did, but the main problem is we have to say that the numbers are kind of connected, right? So how do we represent that constraint? This is probably the most difficult part of this code. Consecutive numbers connect horizontally, vertically, or diagonally. And of course, you can write maybe 3 or 4 rules to represent this one, but there's actually a very simple way to do that. And guess what? Is this rule. So let me try to read for you, and but you have to still try to think by yourself repeatedly that whether this makes sense. So here we have, suppose we have filled R1, C1 with X, and R2, C2 with X plus 1. Right? So these are the two consecutive numbers. What we want to do that, what we want here is R1 and C1, R1, C1 position, and R2, C2 position should be connected either horizontally, vertically, or diagonally. And there's one single equation that tells you how to do that. This one. So what does this mean? Well, if you have the position here, okay, the next number can be either here or here or here, right? Now, if you look at the distance between these two positions, you can see that, suppose this is R, C, and the next position is R1, C1. So it could be either horizontally or vertically or diagonally. But wherever the case is, you will see that the distance between these two coordinates is bounded by square root of 2. So you can see that here, R1 minus R square plus C1 minus C square is bounded by square root of 2. Okay? And I don't need the square root. I can actually square both sides, so we can delete these things. Then you get this one. Okay? Note here that this double star is the exponent. Okay? So R1 minus R2 square plus C1 minus C2 square is less than or equal to 2. So for instance, if I play with maybe this position here, then this is distance is actually R2. So suppose we have here, this is 2, goes 2 in the horizontally. Okay, so then this is actually not less than or equal to 2. What is it? It's 4. right? So this position minus this, okay, square it, you get the 4, and 4 does not satisfy this. So only the nearby, either horizontally or vertically or diagonally connected places will satisfy this equation. Okay? If that is the case, then these numbers should be consecutive to each other. All right? So this is a bit complex because it uses some mathematical equation. It's okay that when you write a program, you don't have to write always succinctly. You can actually try to be a bit verbose, but if you can understand better, that's fine. Okay? All right. Okay, so the next one is, in this puzzle, there are some given numbers, and then the rest of this is what you have to fill in. So initially, we have some numbers that are given. So when you have the given numbers, this is a subset of the numbers that you have to fill in. Okay, that's what this rule is saying. And this is it. So given was, in the previous example, we have 1, 1 position, 6 was given, and 2, 2 position, 2 was given. And you have to fill the rest of it. Okay. Let's see whether we can play here. Okay, so this is the code that you just saw. Yeah, okay. So this is the first problem that we saw, the 3x3 grid. So 1, 1 position has 6, 2, 2 has 2, 3, 2, 3 has 8, and so on and so forth. So we have two programs. One, the basic rules, another, the instance program. So I just use two files as an argument for Clingo. Well, I should actually give the grid size, which is 3. So then I get this solution. Okay? In fact, there should be only one solution. Oh, there are two solutions, actually. I didn't know. There are actually two solutions for the puzzle that we saw first time. Okay? All right. All right, so then let's actually talk about the last feature of the Clingo language here. So in the number snake example, we saw the anonymous variables. And the basic idea, as I just said, there are some rules that are not used in, some variables that are not used anywhere else. So here, for instance, we have R1 and R2 used multiple times, or at least 2 places. But C1 is not used, or C2 is not used in anywhere. It only appears one time. And in the second rule, we have R1 and R2 appear only one time. In this case, we can actually make this as anonymous variables. Okay? And that's it. Because these variables replace occurs only once in the rule, their names are not important. So we can just do this. In practice, this is actually interesting that you can avoid some issues with the Clingo, that Clingo sometimes say the rule is not safe, but if you use anonymous variable, you can solve some of that problem. Here, the rule is saying that you have to choose P1, the subsets of P1 and P2. Okay, but the next rule is saying that you should keep everything. Okay, so it's not the case that you are omitting any of the P value. Okay. Actually, no, I should say that this is actually anonymous variables. So, okay, let me say it again. So the first rule is saying you have to choose from the subsets of P1 and P2, right? How many subsets are there? If you look at only the first rule, how many stable models will be there? 4. Okay, so subsets of the 2 element set, there are 4. But then the next one is that you should not have all these things empty. Okay. So if you look at this one, the Clingo will return this one. What is being removed is the empty set, because empty set doesn't contain any of the P. Right? So that will be eliminated if you use the second rule. And you don't have to know this, but technically this anonymous variable is actually replaced by some auxiliary variable. Okay, and the place that you have this underscore, Clingo actually puts any auxiliary name. Okay, and this is aux predicate, and that's what you do. So in terms of Clingo, it actually returns this program using the aux, but if you forget about aux, the solutions is the same as before. Maybe this is too technical, so you don't have to know too much about it. But basically, if you don't care about the name of the variable, you can just use underline. Okay, that's it. All right. Okay, so the next item is actually aggregate, but I think it's a good time to stop. Any question about today's material? Okay, then let me open the exit ticket.